Here's a quick walkthrough of one of the problems you've likely seen. The key thing here is they give you position, and oftentimes if they give you an equation that looks like it, does that really represent that person pulling on that box? It just seems a little bit contrived. They're setting you up to either take the integral or derivative of something. And since you're already starting at the top with position, you're probably going to be asked to take the derivative of that. And you could probably start doing that knowing that's going to be coming into play somewhere down below. That's a time-saving trick. Well, determine the speed at time t equals 0. Well, if we take the derivative of that position formula, we're going to end up with our velocity. And what we get there is we end up getting 1.5 t squared plus 2. So now that we've got that, that's going to be our velocity. And at t equals 0, well, that clearly equals 2 meters per second. So there's our solution for the first one, 2 meters per second. Determine the following as a function of t, the kinetic energy. Well, the kinetic energy is 1/2 mass v squared, but it wants it as a function of t, so we need to replace v with t, and we can easily do that. We've done that. It's already set up for us. So we take that, and we say, okay, well, 1/2 mass, and then our velocity squared. And that would be our kinetic energy. Now you have, I think the mass is given to you, 100 kilograms. So you could calculate that out and clean that up a little bit, but there you go. The net force acting on the box, the net force, well, we already took one derivative, and we ended up with the velocity. Whenever you see force, think force, you can really always go back. You can always go back to Newton's second. And we know that, okay, well, if I take the derivative of that function up here, I can probably figure out my net force acting on it. And that's going to be the derivative of the change of my velocity with respect to time of 1.5 t squared plus 2. Okay, and that is going to be 3t. So that's my acceleration. And then I'm going to have my force then is just going to be F equals 3 mt, and that would be newtons, and that would be 300 t when you plug in the mass. So there's our net force acting on it. Now you might ask, well, what about friction? What about all those other things? And what they do here, when they give us this, they bake in the idea of that includes the net force. So that's going to include the forces for this problem. So air resistance, whatever, they've got it all in that contrived formula that they made up for us. The power being delivered to the box. Well, the power being delivered to the box can be thought of as either the change in work with the change in time. That's one way to do it. But I think set up even easier for us is the fact that it's also equal to the force times the velocity. And there's no angles to stress about here because all of that force is in line with the motion. And so our cosine of the angle would be the cosine of 0 degrees. Okay, so we would have, all of that. All of that force is in the direction of the velocity. So we just need to take the product of our velocity equation and our force equation, and that's just going to be, I'll write that down here, so this would be BIII, and that's going to be 1.5 t squared plus 2, there's our velocity, multiplied by our force, which is 3 mt, and that's going to be our instantaneous power. calculate the net work between those intervals. Okay, well, the net work, let me move this out of the way. The net work is going to be equal to that force over that displacement. And we're going from time equals 0 to time equals 2. We have an issue here because we've got dx in there and we have time in seconds. So our time is in seconds, and we're not talking about meters from 1 meter to 2 meter. So we need to do something here. So we need to replace that dx. Well, v is equal to dx dt, which means dx could be thought of as v dt, and I have a velocity equation up here, and they're setting me up for a softball solution. So if I replace dx with v dt, I end up getting the product of the force and velocity, which I believe I just did a moment ago, and integrate that between the time constraints of 0 to 2. I should come up with my net work over that time interval and plug that on in. You've got the 3mt multiplied by the 1.5 t squared plus 2 dt from 0 to 2. Plug that in, that's a constant. So the only variables you have here are that and that. So clean this up before you integrate and get that all multiplied together and summed up nicely. And then when you integrate that, you should end up getting the following. You should end up getting 4.5 mt to the fourth over 4 plus 6mt squared over 2, which then would simplify down to 3. And you are evaluating that between 0 and 2. So altogether, you end up getting 1,800 joules plus 1,200 joules, or 3,000 joules, and that would be our net work. So that was our net work by that force over that interval. Is there anything else to do? Okay, indicate below whether the work done on the box by the student during that interval would be greater than, less than, or equal to the answer in part C. Well, part C, and that was just C that I just did. Okay. Well, C was the network, and the network included the work done by the pulling force of the person minus any other work being done that was slowing it down. So whether it's the work done due to friction, maybe it's a very dense air, who knows, but there's any other kind of slowing down, resistive, overcoming force could be subtracted from that. So, well, the work of the pull then would have to be bigger, so that this person's pulling force had to be greater than the net force. And you could write that out any way you want that. If you just excluded any of the subtractive forces of friction, drag, whatever, use examples that clearly the person's pull would be higher than anything subtracting from it to give you the net. Okay. I hope you found this helpful. As always, please bring good questions, because you're always going to be challenged by new and novel ways to work through the problems and the skills that we've been practicing. Okay, good luck.